better understand the relationship between the lockdowns and the pollutant emissions, we looked at the stringency index, which is a metric of the number and type of restrictions imposed by countries during the COVID-19 period. China, which was at the epicenter of the outbreak, started with a high stringency index, but it started to decline at the end of March. That continued until early May, and then it increased slightly. In China, the NOx emissions at the beginning of the period are substantially lower, about 35% from early January to mid-February. However, the lockdowns coincided with the Chinese New Year, which already had suppressed emissions. Consequently, we estimate about 20% of the NOx emission reductions during that time period were attributable to the lockdowns. These reductions continued through March, but afterwards the emission reductions were reduced by about a third. The emission recovery was heterogeneous, however, with persistent reductions along the eastern seaboard but higher emissions towards the western interior. In Italy, the onset of lockdowns started a little later, but increased at the end of February as infections spread, especially in northern Italy. Lockdown restrictions increased through the end of April. The emission reductions largely followed the index and were spatially correlated throughout the country. The early and persistent reductions were up to 25% through early May. By June, however, central and southern Italy were returning to nominal levels, though the northwest emissions remained suppressed. Relative to China and Italy, the U.S. initiated lockdowns quite a bit later. However, even before then, NOx emissions in the U.S. were already low relative to previous years. This is possibly a consequence of international activity. Most of the states in the United States announced emergency stay-at-home orders in late March. The estimated emissions show declines beginning in late February and early March, before the implementation of restrictive measures, with maximum reductions of about 25% in April and May, followed by a moderate recovery in June. In June, the coastal regions still had reduced emissions, but the central U.S., especially Texas, had a greater recovery. So what is the impact then on these emission reductions on the atmosphere and on air quality? Using satellites and observations, we calculated how much ozone changed as a consequence of those NOx emissions. What you can see here are those ozone distributions, where red represents increases in ozone and blue represent decreases in ozone relative to a control run. And you can see that there's a substantial atmospheric fingerprint. Now, the red values are coming particularly during the beginning of the period over urban regions, because decreases in NOx can actually lead to increases in ozone from NOx titration. However, overall, you can see substantial atmospheric fingerprint of ozone reduction as we go from February through the summer. These reductions are substantial. The global tropospheric ozone burden decreased by about 0.6 teragrams of ozone in February to almost 6.5 teragrams of ozone in June. That reflects almost an order of magnitude in intensification and decline in just over 5 months. Using our NASA satellite observations, we showed that this drop in NOx resulted in about a 2% global drop in ozone. While this number may seem small, this drop in ozone, which just occurred over just 8 months, would take over 15 years to achieve, even under aggressive emission control scenarios as currently envisioned by the IPCC. However, each region had its own distinct fingerprint as a function of where those regions occurred, when those emissions were reduced, and by how much. we looked at this question in more detail. Each of the maps represent the reduction in ozone over time associated with each region. Their fingerprints are quite distinct because of the unique regional meteorology. For example, Africa shows both eastward propagation to India as well as westward propagation into Brazil of ozone anomalies. South America, on the other hand, shows ozone anomalies moving poleward towards the Southern Ocean, in a region known as the Roaring Forties. But that only describes a part of the story. The amount of ozone produced per NOx emitted, also known as the ozone production efficiency, differs based upon the available sunlight for photochemical reactions and the ambient chemical environment. It turns out that between February and June, Africa and South America have an ozone production efficiency up to 3 teragrams of ozone per teragram of nitrogen, which is an order of magnitude higher than in Europe. Not only is the location of emissions important for ozone production efficiency, but also the seasonality and timing. In China, ozone anomalies were actually positive in the early winter months because of NOx titration and lower sunlight, even though the NOx emissions themselves were substantially reduced. As time progressed from winter to summer, when there were warmer conditions and more sunlight, the ozone anomalies flipped to being negative. However, by that time, China's NOx emissions were beginning to return to normal, thereby muting the ozone reductions. In Europe, the lockdowns also started early, and therefore the emissions were substantially reduced. But the increase in negative ozone anomalies that we see was a result in part of the factor of 2 to 3 increase in ozone production efficiency, thereby making the impact of emissions reductions more efficient in the summer months. However, the greatest reductions came elsewhere. The largest contributor to the ozone reduction was from Asia, excluding China. It was about 1 to 1.5 teragrams of ozone, which is a little over 20% of the total ozone reduction. The atmospheric signature is quite distinct, with the epicenter at the equator. Strong convection lofts emissions into the upper troposphere, where ozone is efficiently produced and where the lifetime is much longer. That also means that emission reductions have a much bigger impact. In particular, over southern Malaysia, ozone dropped by up to 10 parts per billion, though regionally the average was about 3 to 5 parts per billion. In the tropics, ozone in the upper troposphere is a very efficient greenhouse gas. Consequently, the COVID-19 lockdowns also had some impact on climate as well. As we saw in the stringency index, the U.S. started reducing its emissions a bit later, closer to April. While the U.S. is well developed like Europe, it's closer to the equator with an ozone production efficiency that is 2 to 3 times larger than Europe. The combination of a higher ozone production efficiency and large absolute emissions reductions later in the year meant that North America was on par with Asia with an ozone reduction of 1.2 teragrams of ozone. The ozone anomalies are especially large in June. The signal is readily apparent in the annual anomalies in satellite data. For example, ozone produced by the NASA TROPES project showed in the western U.S. reductions of 10 parts per billion in June 2020 relative to June 2019. It's important to note, however, that ozone anomalies from different regions mix. For example, the ozone anomalies from Asia propagate to the U.S. and arrive, interestingly, at a lower altitude than the anomalies from local emissions. This shows that understanding the complex vertical three-dimensional structure of ozone is important, and it furthermore shows that pollution is a global, not simply a local challenge.